This video was prepared for Engineers Without Borders in partnership with Live and Learn Vanuatu. The EWB Challenge program commenced in 2007 and is focused on improving the living conditions in developing countries through engineering. Espiritu Santo, a remote community on the northeast of Vanuatu, is a developing town faced with several troubling issues that are limiting its ability of social and economic expansion. One issue in particular is the reliance on outdated drying systems to dry copra suitable for sale. Copra sale is a primary income for many communities, such as Espiritu Santo. Current systems, old and ineffective, limit the quantity and quality of the copra produced, and substantially delay the profit available. As a consequence, parents struggle to meet the financial demands of school fees and other costs where copra sale is their primary income. The aim of the project is to increase the efficiency of copra production through improving on the design of the outdated dryer currently in use. The specific problem the project aims to solve is decreasing the time taken during copra drying, increasing copra quality, and decreasing health hazards with the new improved design. Through a series of workshops, the community will be educated on the process of operation to allow them to meet their financial demands.
Problems that the communities of Vanuatu are facing is that their copra dryers are not very efficient in how the copra is dried. Currently, it will take about 3 days. Current demand for the people of Espiritu Santo are to reduce the drying time and time required monitoring the dryer. The new design made substantial improvements on the current dryer, including the use of insulated materials to improve drying conditions. Using such materials would allow for greater heat transfer from the fire pit to the interior airlock between the drying racks and the fire drums. Consequently, the drying time was decreased by approximately 12 to 16 hours. A heat spreader was also placed under the lowest drying rack to evenly distribute the heat across the drying racks. This means the time required to monitor and turn the copra is reduced as all copra is evenly dried. The operation approach was improved by recycling the coconut shells as a fuel source and providing a design that is scalable to the needs of the community. The use of more robust materials, cement, clay bricks, treated wood, allow for the structure to withstand significant greater forces, like that experienced during storms and hurricanes. This improved on from the worn-out light materials used in the old design. An initial design matrix was created to determine a solution to this problem, with the weightings for the design requirements based on the indicators of appropriateness, as determined by the local community. EWB conducted surveys across Espiritu Santo to determine what the community decided was important in the project. The design requirements include the cost of solutions, the amount of community input, materials needed for construction, possible income increase of producers, and a short and long-term maintenance required. The solution that was chosen from the design matrix was to design a new dryer for the community to use. This solution was most appropriate due to being the highest rated in relation to the design requirements set by the group in the design matrix. Another design matrix was created to choose the final design that our dryer would be based off. Like the previous matrix, weightings were chosen from the indicator of appropriateness image. The design requirements were efficiency, cost of the materials, long and short-term maintenance, reduction of waste, community controlment, and amount of income generated, as well as if the materials were local. The modified Tonga kiln design is the most appropriate final design.
To represent the design of the project, a scale prototype was made using the visual design software Autodesk Inventor. The design that was chosen focused on improving the speed and safety of the current copra dryer. This was ensured with improvements made to the fire drum, which was pitched on an angle so that all the smoke would be funneled through a chimney and away from people. The drum was also lowered into the ground to keep people away from the high temperatures and possible burn risk of the burner. The time for the copra to dry was decreased by enclosing the copra in a wooden structure during the drying process. Along with the use of insulating materials for the housing of the copra and burner, would help to significantly decrease the time for the copra to dry. To further improve the speed of the dryer, buffer plates were added above the dryer to help direct the heat of the burner towards the layers of copra being held by racks in the structure above. The roof of the structure was also slanted to allow heat to be filtered through another chimney. This will help keep the dryer from retaining large amounts of moisture and slowing the drying process. Using this improved design and the Inventor software, it allowed us to print and test our design for any structural flaws. using the inbuilt stress analysis software. This analysis was done by applying the forces of the highest recorded wind speed that Vanuatu had experienced. This force was found to be around 14,000 newtons. After properly constraining the model to account for the underground sections and gravity, the force was then applied perpendicular to the roof, chimney, door, and structure. After properly constraining the model to account for the underground sections and gravity, the force was then applied perpendicular to the roof, chimneys, and door and structure's body to simulate the max force these sections would experience.
During the CAD prototyping, it was discovered our initial plans to support the roof were not durable enough to support the weight. As a result, during the stress testing of our prototype using Inventor, the supports would collapse under the weight of the roof. More wooden support structures were needed to be added to ensure the dryer remained standing in extreme weather conditions. The wooden support structures needed to be extended into the concrete to prevent them from collapsing. It was found that when the stress was applied to the tall chimney, it could not support itself. A brace was needed to connect the two chimneys to strengthen it. Once the prototype was completed, the final dimensions of the dryer were confirmed to be 8 meters long, 2 meters wide, 2 meters above ground, and 2 meters below ground.
Implementation of the dryer into the Espiritu Santo community is an important stage in ensuring a new dryer is a viable solution to solving the problem. The dryer will be implemented through a series of interactive workshops. The first workshop outlines how the dryer is constructed and operates, including the operation of the various drying racks and the importance of maintenance of the fuel system. The first workshop will then elaborate on the importance and benefits of using locally available natural resources to construct the dryer. This will include exemplars of recycling the coconut husks for fuel and coconut leaves for walls and roofing. The second workshop involves the community and a senior engineer constructing the dryer from foundations. Included is the excavation of the surface to create the fire pit and construction of the various components. Further, the engineer will provide methods for repair and maintenance of individual components of the dryer to ensure that into the future the community can maintain the dryer self-sufficiently. At this stage, the community will then undertake a test operation of the dryer under the supervision of the engineer to ensure that they have the required understanding to operate the dryer safely.
In conclusion, a solution was found to the problem of Espiritu Santo's inefficient copper dryer, which was affecting the community's quality of life. This was due to the labor-intensive nature of the dryer, the unsafe building materials, and high-risk operation methods. To find this solution, the community was consulted and engaged in every stage of the design to ensure its appropriateness. A prototype was created to test the design and a stress test was conducted. The community awareness and a participation allowed a design matrix be created and used to generate an appropriate solution with a culturally sensitive and sustainable manufacturing and implementation plan.